Hi folks, this is the third video tutorial that I'm making to solve the same problem using three different strategies. It's a structure analysis problem, beam problem with an internal hinge, which is to be done in the Catiav program with the Catiav5 finite element program. Now keep in mind that this Catiav program is not very strong on the beam side. However, for those people who are interested in performing FEA in Catiav, at least this is going to be a good place, a good thing to know. It is these tutorials that I'm making are prelude for a playlist that I'm going to make for performing elementary structure analysis problems using the 3D Experience platform. But I felt that it can also be beneficial to the CATIA user community. The tutorial 1 and 2 in this particular playlist, which are related to strategy 1, strategy 2, and strategy 3, are all solving the same problem but using different approaches. This particular problem is, well, the big thing about it is to model that internal hinge. That's what I want to show how it's achieved. This is a problem out of the Hebler structure analysis problem, the calculate or textbook, and the calculation deflection, vertical deflection of the point B, the internal hinge, will come out to be 4.58 inches approximately if one is doing it analytically. Now, in the last three slides, I'll show you the same slides that you saw in tutorial 1 and 2. Basically, it displays the steps in order to calculate that deflection using analytical solution, principle of visual work. We're not going to dwell on it because that is not really the focus of this particular tutorial. All we want to do is to make sure that we get that 4.58 inches, the internal hinge. And the strategy is different in the following sense. In tutorial 1, I broke this thing down into three lines, left line, middle line, right line, and then joined the left line and the middle line so that I have one piece. And when I measure, there will be a breakpoint exactly halfway in between that I can apply load on it. And of course, over here, for the internal hinge, I use the rigid connection feature. In tutorial 2, I did not join the left line and the middle line. Instead, I created created three separate lines and created two connections, one between the left line and the middle line, and that all the degrees of freedom are transferred. And then there's a rigid connection between the right line and the middle line where the internal hinge is created. In this particular problem, in this particular video, I will make a single line, which I call a left line, 24 inches long, and I'll show you how to actually make sure that there is a place here that you can apply the load exactly halfway in between. And the rest of the problem is the same as before. In other words, you the right line and then measure and then create a rigid connection and release the degrees of freedom. Okay. Now the only thing is that if you have a single 24-inch long line here and you measure, yes, there will be nodes on this line, but you will not be able to actually place a concentrated force at those nodes. However, if you go to the advanced meshing tool and use essentially the projection of a point that was created onto that line, guarantees that there will be a load, the node there, and you can actually place the load on the point and it will be transferred into the node of the beam. Okay, so this is a requirement if you want to make sure that there is a point here that you can actually place a load on. Okay, all right. So let's go ahead and do this. Let me get rid of that and that. All right, let me start with the part file. Okay, and create my left line, basically a line using a point and direction. And I'm going to create my point 0, 0, 0. And for direction, I'm going to use the y direction and a total length of 24 inches. 24 inches. Sorry, 24 feet, not inches. Double click 24 feet. 24 feet. Let me make sure that I did put 24. Yep, I guess let me try it again. 24 feet. Yep, okay. So we have a line here, and then we'll do another line starting from this point in the direction y, and it's going to be 15 feet. Oops, 15 feet. Let me see what I typed in. 15 feet. Okay, good, good. I will create a point off this line. That's to determine the orientation, to specify the orientation, but making it 2 feet in the x direction. So this point, let me make it actually more than that, maybe 8 feet. This is going to be used to set the orientation, and I will create a point on this line. It doesn't have to be on this line, as long as its coordinate, for example, make it on that line. But it's easier if I actually did it exactly on that line. I say a point on a curve, on this curve, and the distance exactly halfway in the middle. The distance will be 12 feet. So you can see a point has been created here. Now, let's apply our material. So we're going to make this thing out of steel, as I have done in tutorials 1 and 2. It's exactly the same steps. I'm going to change slightly the Young's modulus so that it matches exactly what we have in the PowerPoint. Right, it's all done. Now, because I need to make sure that this point will be respected as a node, I cannot go ahead and use this to the generative structure analysis in the usual way that I've done in tutorials 1 and 2 and mesh this thing. What I have to do is I'm going to go to the advanced meshing tool, right there, advanced meshing tools, static, and notice that we have the option of doing beam element right there. You click on it, you select this. I decided to use 1 foot for element size. Now notice that this thing is not available. These things are not available if I had gone to the generative structure analysis. But in advanced meshing tool, you can make sure that a particular point, isolated point, is actually going to become a node. So I'm going to click on that, and it says, what is your support? The support is this point. There's a tolerance that you can specify too, but that's good enough. So this is fine, and say okay. Now I can assure you that this point is going to be a node, and later on when you apply a force on that point, that node will inherit it. Okay, the rest of the problem is just like before. You have to get out of here, you have to go to the generative structure analysis. The rest of the problem is exactly the same thing. Okay, oh, by the way, I forgot to mesh this side. Let's go back here. Let's go back, because I forgot to mesh the other piece. So here it is. Now I could have done it in the where I was generative structure analysis, but I decided to go back and say okay. Okay, now we're going to go to generative structure analysis. Rest of it is the same. In fact, if you say show me the mesh, it shows you both of them are going to be present, and that point, if I say hide and show, that point is going to be actually a node location. Oh, let's deactivate this. See what it did? It took that point, projected it into the line, and made sure that it's going to be a node. That's what this thing is saying. Right click, hide it or deactivate it. Okay, good. Now, let's apply the 1D property just like before. You select this. For orientation point, you select that. It lines these up. For the wrench, this was 30 inch to the 4. That's the bending, a second moment of inertia about the local y-axis. That's where the bending is taking place. See that? Y-axis. It's not this y-axis because these are all referring to the local coordinate system, which is bending about the y-axis. And we say OK. And we say OK. And do the same thing for this guy. So 1D property for that fellow. For orientation point, we select the same thing. And the number is going to be the same, of course. Say OK. All right. The rest of the problem now. Let's clamp this in. OK. Apply user-defined restraint here. And this was a roller. It can move in direction Y, and it's free to rotate about the global X. OK, very good. Now, create the connections. And all I have to do is to do it between these two. Okay, so let me hide that. First component this, second component over there. Okay, if you want, you can bring this into show mode. All right, and now we're going to go and make this thing rigid connection. So that's support, which was analysis connection here, right there. Transmit degrees of freedom, just like before. Now this one should be allowed to transmit the rotation, not translation, rotation 1. Okay, so basically rotation about the x-axis from this side and that side, they're not transferred to each other. Okay, so basically it becomes an internal hinge. And then we say okay. And now we're going to put a force here. Well, let's do the moment first. Moment about this point. It was minus 360,000 pound force inch. Actually, it was 30,000 pound force foot. And if you multiply by 12, you're going to get 36,000. So that's where the 360,000, that's where this is coming from. And the direction of it is correct too. If you zoom in, you can see that it's the correct direction. The arrow points this way, just like we're supposed to. Otherwise, you flip this plus to minus, but it is correct. You don't have to do that. And now, when I put a force of 8,000 pounds on that point, it will automatically be inherited by that node. So if you have not done this thing with the advanced meshing tool, you put a force on that point, the finite element module does not even see it. So where is that force? On that point, the value 8,000 pound downward. Okay, and then we say okay. We should be good, unless I forgot something. That should be good. So let's go ahead and run it. And the maximum deflection should be 4.8, right there, 4.58. And if you look at the view from the side, from the front, you see that kink there. So I have done this problem using 3 different strategies. And the video tutorial playlist that I'm going to create for 3D experience, it will also be what I've done here, plus a few more strategies that are not available to you in the Catiav program. All right, good luck.